Welcome back to this explainer, brought to you by Forge College. All right, so in our last lesson, we tackled integer types and number basics. Today, we're taking those integer comparisons and translating them into the ultimate binary decision makers in Solidity, Booleans. We are going to learn exactly how to gate your smart contract logic with absolute ruthless precision. Let's dive in.
Here's the quick blueprint for today's logic circuit explainer. First, we'll meet the Boolean. Then we'll look at logical operators, followed by a really cool trick called short-circuiting. After that, we'll prove it with actual code and wrap up with some key takeaways.
All right, part 1. Meet the Boolean.
So think of a Boolean as a ridiculously strict bouncer at the most exclusive smart contract club in Web3. I mean, you are either on the guest list, which is true, or you are out, which is false. There is absolutely no gray area here. Now, if you're coming from other programming languages, you might be used to implicit conversions, where a number like 1 is considered truthy and the 0 is falsy. Well, Solidity doesn't play that game. If you want to check if a number is greater than 0, you have to write out that explicit comparison. That comparison then spits out our strict bouncer, a Boolean, which you can then use to allow or deny actions in your contract.
Moving on to part 2, logical operators. So, how do we actually combine these true and false values to make complex decisions? Well, we can visualize these operators just like electrical circuits. First up, we've got the needy AND operator, which we write with 2 ampersands. It's demanding. It literally requires both the left side and the right side to be true. Think of it like a series circuit. Both logic switches have to be closed for the current to flow at all. On the flip side, we have the incredibly easygoing OR operator, written with 2 vertical pipes. It only needs one side to be true. This is your parallel circuit. As long as just one single switch is closed, the power flows right on through, and the whole statement evaluates to true.
And hey, we definitely can't forget the contrary not operator, represented by a simple exclamation point. This operator acts like that one contrarian friend who just flips whatever logic you feed them. Handed a true, it flips it to false. Handed a false, boom, it's true. It is incredibly useful for quickly inverting conditions, especially when you're writing require statements to double-check that a contract is, say, not paused before you allow a token transfer. Part 3, the short circuit trick.
Okay, here is where the Solidity compiler acts like a brilliantly lazy, highly efficient worker. It always reads logical operators from left to right. Step 1, it evaluates the left operand. Step 2, it tries to make a decision as early as humanly possible. If the compiler can figure out the final answer just by looking at that left side, it short circuits. And step 3 happens automatically. It completely ignores the right side. So why do we absolutely love this lazy behavior? Because it saves gas, of course. If the needy AND operator sees a false on the left, it already knows the whole thing is going to fail. So it stops right there. If the easygoing OR operator sees a true on the left, it knows the whole thing succeeds. Again, it stops right there, saving you precious computational resources. Which brings us to part 4, proving it with code.
Now, to prove this short-circuiting isn't just some abstract theory, let's look at a really clever experiment. We're going to set up a public counter variable as sort of a tripwire. We'll place a function that increments this counter right on the right side of our logical operations. If the right side of our logic circuit actually executes, the tripwire gets triggered and that counter is going to go up. But if Solidity short circuits, like we just talked about, it'll skip the right side entirely, completely missing the tripwire, and our counter stays exactly the same. It's a perfect observable side effect.
So, here's the technical blueprint of what we expect to happen based on whether our tripwire is triggered or not. We've got 4 functions here, basically testing the different combinations of AND and OR, with left sides being either true or false. If you take a look at the expected counter column on the far right, that tells us exactly when the right side of the expression is expected to actually run. Let's look really closely at the outcome for AND left false. Notice how after calling it, the counter stays at a massive 0? Well, why is that? It's because the left side was false. The needy AND operation immediately short-circuited. It didn't even bother looking at the right side. Because of that, our tripwire was never crossed and the counter remained totally untouched. This literally proves that the gas-saving skip actually happened in real time. Conversely, let's look at OR left false. In this case, the easygoing OR operation looks at the false on the left side and basically says, hold on, I can't give up yet. If the right side is true, we can still pass. So it literally has to check the right side to be sure. And in doing so, it steps right on our tripwire, which trips our counter up to 1. The execution of the right side is completely verified.
And finally, part 5, key takeaways.
Let's wrap up our logic circuit design with some absolutely crucial rules of the road. Remember, Solidity is incredibly strict. You aren't going to find implicit numeric conversions to Booleans here like you might in Python or JavaScript. Always use explicit comparisons to produce your true or false states. Keep in mind that your and or operators evaluate left to right, and they will short circuit to save you gas. And lastly, whenever you need to test these behaviors in your own local environments, use an observable side effect, just like our counter tripwire, to prove what code actually executed.
So if you take nothing else away, keep this simple engineering mantra in mind. And means both must be true, while or means at least one true is enough. Burn that into your memory as we prep for our next lesson, where we're actually going to apply these exact Boolean checks to address types, doing things like verifying non-zero addresses and building out safe transfer guards.
So what do you think? Are you ready to take these strict bouncers and use them to lock down your own smart contracts? I certainly hope so. That brings this explainer to a close. Just a quick reminder, this explainer was brought to you by Forge College. Make sure to head over to forge.college to dive deeper into this subject and explore a massive library of other awesome Web3 topics. Happy coding, and we'll see you in the next explainer.